So I'm here to bring, I suppose, with this kind of a different lens on the whole OAE space, and we've been talking a lot about the application of the alkalinity and the deployment and what kind of effects it may have. But of course, I mean, alkalinity also needs to be generated in a sense, and that's really a bit about technology, and that's what we are talking about right now. So, a couple of years ago, when conversations started to emerge about this whole program, and by the way, I want to echo that I think it is an amazing effort to bring everything and everybody together. So it's a big hand to Carbon to See in that respect. But Antonius asked my colleague Phil Renforth and myself, like, could you do something with assessing technologies? And we said, yeah, we can do that. That's something that we've been doing for a while for different types of technologies. So why not for OAE? Because we want to be able to compare what OAE may, or different OAE approaches may cost, for instance, or what the environmental performance of different OAE approaches may be beyond what happens right there at the location of deployment. So what we set out to do was to develop a first-time right framework for the performance assessment of OAE approaches. And maybe as a bit of background, I myself come from CCUS, and there's been this very long debate on what is the climate performance of CO2 utilization technologies. And for way too long, there wasn't a very good way of assessing that, or at least not a harmonized way. And that basically led people to make the wildest claims about what CO2 utilization can do in terms of climate impacts or climate benefits, which wasn't true. So that's an issue, right? Because as a government or a funder, they want to know what to invest in, and talking about investment, especially investors want to know what to invest in. So then, what we do a lot is something called technology and systems assessment. And that's really basically the investigation of how a technology or a system may or will perform in a real or a hypothetical operating environment, and given an assumed set of boundary conditions. And I think this is just a very important notion to start with, because this is about may or will. It's about real or hypothetical, because you always, when you do these kind of assessments, you need to make assumptions, and you need to make simplifications, and so on and so forth. And it really depends very often, right? It depends on location. It depends on what electricity prices may be. It depends on the availability of alkalinity in the location where you want to, of materials to generate alkalinity in the location where you want to deploy it, for instance. So there are loads and loads of ifs and buts. And then, you can do this from a technical perspective. So, for instance, take a process that generates alkalinity, look what the mass and energy balances are, for instance. Look how efficient it is from an energy perspective. You can do it from an economic perspective, from an environmental, and also from a socio-economic perspective. And I should have probably said social and political rather than socio-economic. That's a bit of an oversight from my end. Now, why would we want to do technology assessment or systems assessment in the first place, right? And that's, that's probably a very good question, but investors, for instance, or funders will probably have an answer to that. But some of the reasons may be that we want to know how technologies or approaches compare in efficacy and efficiency. Right, so we ideally, in an ideal world, we want to put our effort into approaches that really work best, or technologies that really work best, and maybe forget about the rest. We also want to know where to best locate a project, and with OAE, that's very dependent on so many different variables. It depends on the OAE efficiency locally. It depends on social and political elements. It depends on the cost of electricity, but also how clean or dirty that electricity may be, because if you have to put a lot of electricity in that comes from coal power, for instance, or from a very dirty grid, then maybe you may emit a lot of CO2 while generating the alkalinity, right? Where are improvements still needed, or what type of improvements are still needed? And for instance, what type of government support may be needed to make this happen? Because let's be honest, there isn't a natural market for climate change mitigation, so many of these things just need support. and especially support in early years. Now then another question that you may have is, so who would do these kind of technology assessments? And really there's quite a few organizations who would do this, right? So there may be industries doing this, academia does a lot of this, but also consulting and engineering firms. Audience types vary, they can be executive boards, they can be investors, they can be academics, etc. And the purposes can also be very different. So for instance, an industry may do technoeconomic or life cycle assessments, for instance, to inform their executive board who need to make investment decisions. Are we going to invest in this technology, yes or no? Or to do master planning. So if they want to have a strategy for the next 10 years, they want to know what the options are, and they need to know kind of how their portfolio of investment should look. Similarly, another audience that's really important is policymakers and governments, and we talk quite a lot with them or to them, and that's good. It could be more, I suppose. And for instance, us academics can do these type of analyses to help them understand how well certain technologies may perform and where they may need to channel their money and investment into, right? Now, just as a little bit of background, so I've been in this field for about 12 years, and where you always start is with kind of the textbook methods, right? I'm a chemical engineering graduate. In year 3 or 4 of your chemical engineering degree, you start to do design studies, and you start to learn about how to cost a project. But textbook methods are by default for existing technologies. Remember that. Where mass and energy balances of the process at commercial scale, so not at pilot scale, not at TRL4, but at commercial scale, are known or knowable, where supply chains are established and feedstock costs and environmental impacts are known or knowable, and where tax, policy, environmental and regulatory frameworks are known or knowable. And this is then what we call textbook methods or classical methods. Probably none of this is true for OAE or for any other CDR technology at TRL4. And this really poses a big problem. So because what happens a lot, and you see that in the scientific literature, you see almost every and any startup make the same mistake, is that they do a very rudimentary TEA, for instance, and say, my technology costs X. And by the way, it's always lower than what DOE Nettle wants to see. And by the way, it's probably never possible, because DOE Nettle sets their targets very low for a reason, because they want to drive innovation towards that. And they know it's unrealistic. But this is a massive issue, right? So for OAE and many other CDR technologies, we do what we call ex ante technology and system assessment. And that means ex ante means nothing more than before the fact. So it doesn't exist yet. We don't have a commercial OAE project. We have a few commercial direct air capture projects, but even those are at very small scale, right? We have forestry is commercial that we know quite well, but for many of the other CDR technologies we don't. Okay, I'm going to skip through this. Basically, the bottom line is we know nothing. And then this one is also interesting. Very few people know this. So when you are this is the same whether you are a scientist or whether you are a startup, because we are all optimistic, we're all technology optimists, and we all believe in what we're working at. So when you are, for instance, at a research or development stage, and you make a TEA, or like a cost analysis, or for that matter, a life cycle assessment, then the estimated cost or the estimated resource use or the estimated emissions per unit of capacity are usually quite good looking. They're usually quite low. But as you progress, so you start to build your first pilot plant, and I've just been through this with electrochemical system for carbon capture. We went from TRL4 to 7, which was too big of a leap. But anyway, so yeah, it's just, you can't beat the reality. But so what you start to learn is what it really takes to make your process work at the capacity and at the functionality that you want it to work. And you also start to understand where you've underestimated everything, and costs only go up. They always go up. So then you've built your pilot, and you're like, oh, cranky. This is actually a little bit worse than what we expected, but we're going to engineer this out. And guess what? Engineering out problems costs money, because you have to add equipment, and you have to add redundancies, and you have to add capital, etc., etc. So by the end of the day, when you're finally ready for your first deployment, your cost estimate has actually gone up by quite a lot. Costs don't go down, as so many companies tell you, from startups, from TRL4 to TRL9, they go up by quite a lot. That isn't the problem. That's normal. That's the reality. But we need to embrace that reality. And I think companies who've brought technology to market know that. The thing is that most startups haven't, and they don't have people on board who have that experience. Now, the good news is that from the first of a kind, the first time you build like a large project at scale, you will start learning how to do things better. You will start learning how to replicate things. Maybe some elements can be mass manufactured. Maybe some things can be done smarter. And by all that replication, your costs are starting to fall. And this is what we call technological learning, or experience, or things like that. And by the time you've reached the gigaton scale, yes, you will be much cheaper. And that's the good news. But there's this hurdle that you need to get over. So this is an example of for instance, the type of realities that you face when you work with ex-ante technology assessment. Now, so in response, and this was actually, I think we went beyond what we were initially trying to do, but in response, we developed what we think is a first-time right OAE assessment framework to kind of circumvent some of the issues that we've seen with so many other climate change mitigation technologies. So we start from the contemporary, and that is static, right? We can do our analysis for the first of a kind commercial scale plant. That's what we can do, and that will be static analysis. It will be for 2024 or 2025, if you will. And you have a look at what does the technology do now. So that's kind of your foreground system, and how does the environment or the context of the technology perform, and that's your background system. But that's not what we want to know, because we're not going to deploy these technologies at scale now, are we? So what we're really going to do is deploy them in 10 years from now, if we're lucky, or maybe 20, or maybe by 2050. So we do that by prospective life cycle analysis, and something we've developed through the Carbon to Sea grant is also prospective technoeconomic analysis. And we had some things in place to do that, but we've been able to make a good, comprehensive, and holistic framework for that. So the framework is consistent with technology RD&D dynamics. It's rooted in technology market adoption theory. It's aligned with relevant IPCC scenarios. That's how we look into the future. So we have to choose a scenario that we find relevant. Now, a 3.5 degree temperature increase scenario is not relevant for us, because then CDR is not needed, but 1.5 or 2 degrees C will be much more relevant. It is explicit in time and location. So the framework can tell you in which country you can best deploy your alkalinity project. And it embraces uncertainty. So rather than saying, my technology does X and that's the truth, it embraces the fact that you don't know, and that uncertainty analysis is really important. So just a little advertiser. We have 3 posters, numbers 3 to 5, and if you want to know more about the framework, then by all means come and stop by later. So I'm going to exemplify this, and I'm going to exemplify this with bipolar membrane electrodialysis. And the reason for that is that most of us are, I'm from a chemical engineering school. This is the most engineered kind of OAE application, but we won't stop there, right? So we've already moved on to new case studies, but this is for exemplification, because that helps to understand how certain things may work. So we have what we call a base case, where we take seawater. We do a lot of pre-treatment. You need to do a lot of pre-treatment before you can even start thinking about putting that water in your ED unit. We do something called softening, so taking out all the ions that we don't want in there, and then we generate from the soften and the cleanup water. We generate the alkalinity. So that's our base case, where all these steps are needed to generate what we, our end product, which is sodium hydroxide. There are perturbations to this, of course, that you can implement. So one of them is, for instance, you do your softening through nanofiltration, which is a bit smarter process, and it may have different results. You can also choose to do no softening, and this is, for instance, for the case where your ED membranes have been developed to such a standard or such an extent that a couple of divalent ions don't make any difference anymore. Based on the, I'm not so confident that we're there yet, but we may get there at some point. And then the other option is, of course, to not take seawater at all, but for instance, base your product on brine rejects, for instance, or other waste feeds, and then you don't need the softening anymore because that's already been done, right? But then you may run into the issue of capacity because there's a lot of seawater, how do you call that? Seawater making to fresh water in the world, but not as much as we would like to do in terms of carbon dioxide removal. So these are the 4 variants, and I'll show you some. This is really a selection of results. By the way, we have released our framework that is also available with the under the poster. So Carbon2C was kind enough to print a couple. So if anybody's interested, you can take the whole framework. Mind you, it's 200 pages. Okay, so I think one of the messages is that testing different configurations is important, right? So at this point, I think, or if you would want to build an ED process, you'd need to have this water pre-purification and this softening, etc. But maybe in the future you may not need that anymore. So here, for instance, you see the climate change impact of applying this process. And this is kilograms CO2 equivalent per ton CO2 drawdown. And this is for 2024, and it's for Washington State. So the base process emits 1,400 kilograms, 1,500, almost 1,600 per ton CO2 drawdown. That's with the current grid intensity, right? So we don't have a very clean grid at the moment. And then there's the other processes. So no softening, for instance, has a better performance. Softening via nanofiltration has a better performance, and also waste feed has a better performance. What I want to show is that blue bar in the base case. That's important because we use loads of minerals for the precipitation softening, and these minerals are produced with a carbon footprint. Right? And many of these minerals need to be produced by calcining them, and that generates CO2. So this is really important. What we also know, what we also know, but also show with the case studies, that costs will evolve with time due to replication and learning, for instance, and also because energy will go down and capex will go down, right? So you can't assume that the technology of 2050 will be the same as the technology of now, and that's what you see in this slide. So here we give costs only for the base case BPMED, but also for the no softening BPMED. And then what you see is that the aligning with the 2-degree scenario, as for the people who know IAMs, the SSP2 RCP 2.6. This is how the costs will evolve with time, right? So they will go down, and these are the net levelized cost of carbon removal, also for Washington, USA. Yeah. And then another really important one, and there's much more to talk about, but I don't really have that. Well, I could do, but then we don't have time for questions. Another really important one is about location. So we had a good look at the Seaworthy paper, where they include all the locational OAE efficiencies. And we've selected a number of case studies with good OAE efficiency, but also that have cities close by and industrial industries, because you can't build such a project in the middle of nowhere. It's just not going to work. So there are lots of siting considerations that you need to take into account. And then we look, for instance, at climate change impact and at cost of net CO2 removed. And you see kind of a bit of a ranking here, right? So this is for 2024. So you see here that, for instance, climate change impact, Norway would lead. Well, that makes a lot of sense because Norway has a very clean energy grid or electricity grid. They use basically run-of-river hydropower, so that's super easy. And then the cost of net CO2 removed. We have one US, and I'm now wondering, looking at Ronaldo, if this is Alaska or if that's Washington, the one on the top. More likely to be Washington, okay. Yeah, thanks. And then we can do the same for 2050. So you see that the rankings may change. The climate change impact, the UK, starts to lead. And the cost of net CO2 removed, actually, it's also one of the US states that is still leading. I also do want to say that the scales change, so then take the size of the bar for comparison between the years. Again, this is just exemplifying some of the results and what the framework can do. So what is really important is the framework can look ahead in time, but it also can think about timing. So we know that alkalinity doesn't equilibrate with CO2 instantly. Like for instance, if you do direct air capture, you take a CO2 molecule from the air, you stick it on the ground, and that's that, right? The CO2 is buried and is removed. And with alkalinity enhancement, that goes a little bit slower, and it also depends on the type of alkalinity that you add. And we know that, for instance, with forestry, it goes even much slower. So this dynamic is included in the framework, and we give options for dealing with that. And it really depends also, links to markets. I'm not sure, was it your question? Somebody asked about markets before and how to deal with this. So that really depends on how markets want to deal with this. Do you pay already before the actual CO2 is drawn down? Or do you pay only after the fact? So do you want to see the evidence first? That makes a difference in how economic a project is or can be. And are we looking at CO2 drawdown like actual molecules, or are we looking at CO2 drawdown equivalents basically on a time scale, let's say of 100 years or 50 years or 20 years? And all these kind of methodological choices start making a difference in the final result. So this is all in the framework. It's too much to put on slides right now, but I think they are really important talking points for everybody who wants to start thinking about how to monetize these kind of things, et cetera, et cetera. Okay, so this was kind of our first case study, and the case study that we used to exemplify, our thinking on how this can be done or should be done. We've started 4 more case studies to kind of capture the breadth of approaches available. What we will do is refine the framework with insights from these case studies, and I'm pretty sure that we will have new insights because that always happens. And we'll also do loads of dissemination because to get the word out. And that's me. One question? My monitor says at least 2. Any questions? I have a couple of questions. If you get the microphone to the middle table, there are 2 questions there.
Thanks very much. I think this is super important stuff. And it's a bit of a shame, perhaps, maybe you're doing this in a different way, but it's a shame not to have direct air capture on that list of case studies, because that's the bench line at which this really needs to be compared, I think, to rule out bad ideas. Maybe you have done this, though.
No, I don't have direct air. You said direct air capture, right?
Yeah, exactly. Because that's the gold standard, right? And this only makes sense if it can beat it.
So I'm a big proponent of direct air capture. I'm dedicating quite a bit of my career to it. I'm not sure if people would say still that it's the gold standard. Yeah. Okay, now I'm going to do a bit of fundraising. I think we need to apply this framework to a whole lot of different OAE technologies. Sorry, CDR technologies and approaches. So if anybody is interested. Mark?
Well, I was just actually echoing the same thing. I think it's absolutely important that we look across all relevant CDR technologies and have understanding and agreement across these various technology areas for a uniform framework that we can really start comparing opportunities. So.
I think the framework is there, and it's applicable to basically any CDR approach. And then what it comes down to is bringing in the relevant knowledge and the relevant, bringing in the relevant knowledge of all these different approaches to be able to start parameterizing it for different CDRs, right? I mean, we have done it and can do it for direct air capture. We can do it for enhanced weathering. But there's also a lot of approaches that we can't do it for, so there we need to team up with other teams. I still have 8 seconds, so he had his hand up first. Oh, now the 8 seconds are gone.
So I spend most of my time in the TRL less than 3 land, thinking about new ways of doing things. And I really liked your chart there. Is there some hope for a better predictability of the nth of a kind cost, which you really kind of want to know really early on? Is it like a rule of thumb, you think of everything you can think of and you multiply by 2, something like?
Yeah, that's a good point.
Like a home improvement project, I don't know.
So there are guidelines for that, and we have based our framework on these, right? So there's a number of studies underpinning these kind of guidelines and factors, etc., etc. So by all means, have a look at the framework, but also at the scientific literature it references. And if you have any questions, I mean, just also give me a call. Thanks. Coffee.